we're going to continue our discussion of the nature of electrons by looking at the particle nature of light. So before the 1900s, scientists believed that light only behaved as a wave, and that was until the photoelectric effect was observed. And the photoelectric effect is that only high frequency, which is short wavelength light, can lead to metals ejecting an electron. That is only high frequency, again, short wavelength, because remember, wavelength and frequency are inversely proportional to each other. So only high frequency, short wavelength light can lead to metals ejecting an electron. So this seemed kind of strange. Why did light have to be at a certain frequency or wavelength in order to cause an electron to be ejected from a metal? Well, Albert Einstein proposed that it was because light is not only a wave, but it can also behave as a particle. And so his proposal was that light could come in packets that he called photons. Meaning that light could also behave as a particle. And Einstein describes this mathematically, and he did that by using an equation. So the energy in a photon could be described as E, and that is the energy in a photon, equals h, which remember is Planck's constant, times frequency. Or alternatively, if you don't have the frequency and just want to use the wavelength, E equals hc over wavelength. So either one of these equations is going to give you the amount of energy that is contained in one single photon. So this concept was really important because it suggested that light was not perfectly uniform, which was very different from what scientists at the time expected. So how does this actually work in like a real practical setting? So here's an example. So let's say we have a nitrogen gas laser pulse that has a wavelength of 337 nanometers, and it contains 3.83 millijoules of energy. How many photons does it contain? So as you can see, we can use the wavelength of the light to figure, and the amount of energy that light has, and figure out how many of those light packets or photons that light sample contains. So let's come up with our strategy here. So we know that we are given wavelength, and we have the energy of an entire laser pulse, and we want to figure out the number of protons. So what we're going to find here is number of photons. So we know that E equals hc over wavelength will give us the energy of one photon. But we don't know the energy of one photon. We only know the energy of all of the photons. So by figuring out the total energy of the photons, and then dividing that by the energy of one photon, we'll be able to figure out the number of photons here. So that's going to be our strategy for figuring out our number of photons. So far, we already have the total energy of the photons. So we already have this value here. It's just given. That's the 3.83 millijoules of energy. So in order to find the number of photons, we need to find the energy of one photon, and we can use that by using this equation. So let's go ahead and do that. We have E equals hc over wavelength. We're solving for E. We're trying to find the energy of a single photon. So that is going to be 6.626 times 10 to the negative 34th joules per second times 3.00 times 10 to the positive 8th meters per second. And then take a look at our units. Notice that the wavelength is given in nanometers, but the units that we need to cancel are meters. So we need to convert that, the nanometers to meters. So if we have 337 nanometers, and we need to convert to meters, for every 1 meter we have 10 to the positive 9th nanometers. And that is going to give us 3.37 times 10 to the negative 7th meters. So that's what we're going to substitute in for our wavelength. And if you want to solve that on your own, go ahead and pause the video here. But your answer should be 5.899 times 10 to the negative 19th joules. And that's going to be the energy of one photon. And if we're taking a look at our significant figures, the smallest number of significant figures we have is 3, so that is going to be a 3 sig fig number. I'm going to underline that for now. So now we know that if we divide the total energy of all of the photons in that laser pulse divided by the energy of one photon, we'll get the number of photons that we have. But notice again that we have an inconsistency between our units. So here, the energy of all of the photons is in millijoules, but the energy of one photon is in joules. So that means we're going to have to do another conversion here and convert that millijoules to joules. So if we have 3.83 millijoules, in 1 joule we have 1,000 millijoules. We will get 3.83 times 10 to the negative 3rd joules, and that's going to be the energy of all of the photons. So now if we substitute this value and this value into this equation that we already came up with, then we are going to get 3.83 times 10 to the negative 3rd joules divided by 5.899 times 10 to the negative 19 joules. This is going to give us the number of photons. So if you want, again, go ahead and pause the video to solve this on your own. And the answer that you should get is 6.49, remember 3 significant figures, times 10 to the 15th photons. And that is going to be our answer to this problem. So that's how you would kind of like use that that photoelectric effect, those photoelectric effect equations to figure out how to solve these kind of problems. So the key point about the photoelectric effect is that it depends on whether the photon of light has enough energy to dislodge an electron. So the important thing about the photoelectric effect is that the light has enough energy to dislodge the electron. And that's going to depend, like how much energy is required is going to depend on how strongly that electron is attracted to the metal it is part of. So we have an equation to describe that. So we have our energy of our photon right here. And that is going to be equal to the binding energy of the electron to the metal. And then when these are equal, then the electron can be emitted. So that's why only the high frequency light is able to emit an electron. Low frequency light just doesn't have enough energy. So what does this mean for us? The important thing, pretty much everything that we've been talking about so far, is that sometimes light can behave like a particle, like when it is dislodging an electron from a metal. Sometimes it can behave as a wave, but we just can never observe both of those properties at the same time. So when we're talking about light as a particle, one of the things that we need to talk about is atomic spectroscopy, which is the study of electromagnetic radiation, because light, the properties of light as a particle lead us to the study of spectroscopy. So when atoms are provided with enough energy, they can emit light. That's kind of what we were just talking about, how electrons can be dislodged from a metal. But any atoms that are provided with enough energy could do this. And so for like an example of one that you might be familiar with is neon. So I think many people are familiar with neon signs. When those neon atoms are provided with enough energy, they can release or emit light. And neon lights are always going to be red. If it's a different color, there's some element in there that is not neon. And when light is diffracted through a prism, so in this illustration here, it results in distinct bright lines that we call an emission spectrum. So this is your emission spectrum, so these bright lines, and it is very distinct for each type of atom that is emitting the light. So this is a way of identifying a type of, like what type of atom you have. But this is really weird, right? Because again, when scientists were first starting to study this, they really only thought that light could behave as a wave. And this is definitely not wave nature. So a scientist named Niels Bohr decided to figure out what was going on here. And so what he figured out, or what he proposed, is that atoms are in fixed orbits around a nucleus, and he called these stationary states. And basically what he believed was that when electrons move between stationary states, they're either absorbing or emitting energy. So when electrons are going from a higher energy state, so for example, this n minus 5, or n equals 5 here, if it were to go from n equals 5 and then move to a different state, so for example, n equals 4, that would be an emission of energy. But if we wanted to go from n equals 4 to n equals 5, then that electron would be absorbing energy. And we can calculate the energy of those transitions using the Rydberg equation. And there are different forms of the Rydberg equation, whether you're using like wavelength, frequency, and which constant you're using. So this is the form that I like to use. This is what I think is leads to the easiest method of solving these. So if you Google the Rydberg constant and see something different, take a look at the units. Make sure that you are in the units that match the equation you're going to use. So this Rydberg equation, if we're using wavelength, is 1 over wavelength equals the Rydberg constant times 1 over n1 squared minus 1 over n2 squared. So notice something really important. This is not final minus initial. This is initial minus final, which is really weird, but that's the way that you're going to have to solve these in order to use this particular version of the Rydberg equation. So let's put this into use. What is the energy of a photon emitted when an electron falls from n equals 4 to n equals 2? So if we look back at our Bohr model over here, then our electron is falling from n equals 4, so here's n equals 4, down to n equals 2. So it's going from a higher n value to a lower n value. So that means we are going to have emission. So we are our photon is releasing energy. It's emitting energy. So the first thing we want to do is we want to use our Rydberg equation. So as I said, this is 1 over, oops, I'm just going to rewrite that. 1 over wavelength equals RH times 1 over n1 squared minus 1 over n2 squared. And when we solve this Rydberg equation, that is going to give us wavelength. But it's asking for energy of a photon. So once we get wavelength, this is our step 1. Once we get wavelength, what are we able to do? We are able to use the equation for energy of a photon to figure out what that energy is. So let's go ahead and get started. So we have 1 over wavelength equals 1.097 times 10 to the 7th, 1 over meters, times 1 over 4 squared minus 1 over 2 squared. And those are our n values. Those values come from there. So notice again, we are falling from n equals 4 to n equals 2. So n equals 4 is our starting value, n equals 2 is our ending value. And when we solve that, feel free to pause the video if you would like to solve that on your own. But you should get a value that looks like this. So negative 2056875. Okay, so this is kind of weird. We ended up with a negative value. Well, we are just going to ignore the negative sign. And the reason for that is because that's just telling us that energy is being emitted, like it's being released. We can't have a negative wavelength. So we are just going to ignore that negative sign and just know that that means that energy is being released by this photon. So if we ignore that negative sign, then this is going to be our positive answer. And then if we solve that for wavelength, then we get 4.862 times 10 to the negative 7th meters. So now that we have our wavelength, we can use that value to figure out what is the energy of that photon. So we have E equals 6.626 times 10 to the negative 34th joules per second times 3.00 times 10 to the positive 8th meters per second. I don't know why it always gets really large right over there. And then divide that by the wavelength that we just found, 4.862 times 10 to the negative 7th meters. I'm going to try to rewrite this just to make it a little bit easier to see. Times 10 to the 8th meters per second. Okay. Okay, I'm sorry, I tried. So if we solve that, we should get .0 times 10 to the negative 19th joules. And actually check my math there, just because I think I might have gotten that wrong, but let's take a look. So H times C divided by 4.862 times 10 to the negative 7th. Okay, so 4.08. Times 10 to the negative 19th joules. And that is going to be the energy of a single photon that is emitted when the electron falls from this level here, this n equals 4 level, down to the n equals 2 level. So also, by the way, fun fact, whenever our final value, so whenever the n final is equal to 2, that light is going to be in the visible spectrum. And so the reason that that could actually be useful is that you know that the visible spectrum is from about 400 to about 750 nanometers. So you can check your work. And so right now the wavelength that we found was in meters. If we wanted to put that in nanometers, then that's going to be equal to 486.2 nanometers. We know it needs to fall somewhere between 400 and 750 because it fell down to n equals 2. And that is true. It is in between 400 and 750, so we know that we have a reasonable answer for the wavelength. So over the course of the past 2 videos, we've been talking about electrons and how we can use the nature of light to learn more about them. So both the particle and the wave nature of light. So why is this actually important? So we want to use or not we want to use, but just like we can observe an so think back to Schrodinger's cat. So remember, we can never observe the cat as being both alive and dead. We can also not observe an electron behaving as a particle and a wave at the same time. And so what that means is, because we can't observe a particle or an electron behaving as both a particle and a wave at the same time, that means we can not observe the velocity and the position at the same time. So why is that? That is because velocity is related to the wave nature of an electron. And position is related to the particle nature of an electron. And since we can't observe both the wave nature and the particle nature at the same time, that means that we cannot observe the velocity and the position at the same time. So we can never know both where a particle is and how fast it's going. So this is really weird, because this is another example of how quantum mechanics is very different from our understanding of classical mechanics. So in classical mechanics, like, we can always predict where an object is going to end up if we know its speed. So I know many of you are athletes, so some of you I know play lacrosse, some of you may have played baseball or softball, maybe tennis. So think about any of those sports. Your success in those sports are determined by your understanding of classical mechanics. You may have never thought of it that way, but it's still true. So what that means is that, like, let's say you play tennis, and the person that you're playing against hits the ball toward you over the net. You know where that ball is going to bounce, so you can run over to that ball and hit it back to the other player. So in quantum mechanics, you can't figure out exactly where that electron, if the electron is our ball, we can't figure out where that's going to go. So in quantum mechanics, we have to depend on just a probability distribution map. Because again, we can't know exactly where an electron is if we know how fast it's going, and if we know where it is, then we can't tell how fast it's going. So if our tennis ball were like an electron, that would be a really, really difficult game of tennis that we would be playing.